Greetings. So, we have developed the idea of what is a Berry phase. So, when a Hamiltonian depends adiabatically on some external parameters, the system evolves, and the usual time evolution, the temporal evolution as we call it, is described by the dynamical phase. The stationary states remain unchanged except for the dynamical phase. But in addition to that, there is a geometric phase which depends on the geometry, and that is called as either the geometrical phase or also the Berry phase. And we also started talking about the Aharonov-Bohm effect, in which the idea is that we are used to thinking in terms of causality, the cause-effect relationships which goes into Newtonian dynamics, and a stimulus is the cause of change in momentum. dP by dt is equal to the stimulus, which is a force. So, that is the idea which is deeply embedded in our thinking, and it is this relationship which goes into the equation of motion, which is F equal to dP by dt. So, in the context of a charged particle in an electromagnetic field, the F equal to dP by dt is described by the Lorenz Force Law. The force is charge times E plus V cross B. So, the force is in terms of the electric intensity and the magnetic induction field B. And if E is 0 and B is 0, we would expect no force, no cause, no effect, right? In the Aharonov-Bohm effect, we have these particles, as you see in this picture, entering the double slits, two slits, and they would generate an interference pattern. But if you keep a solenoid right behind the slit, not so much in the middle between the entrance slit and the detector, but right behind the double slit S1 and S2, then the two electrons which are streaming in from the two slits, they go past the solenoid, and the solenoid is, as we described it yesterday very appropriately, not only long but very long and very, very long, so that all the magnetic field is completely inside the solenoid. There is no B outside the solenoid, and the particles are going around it. Then the particles are always in a space where the magnetic field B is 0, but what enters quantum mechanics is not the classical causal relation, but the Schrodinger equation. Not Newton's equation, nor Lagrange or Hamilton, but Newton's equation, the Schrodinger equation. And in the Schrodinger equation, it is the vector potential which enters, and as a result of that, there is a phase consequence which affects the phases of the particles going around the solenoid. And if you look at this picture, the current in the solenoid is going one way. Look at that arrow on the showing the direction of the current, and the magnetic vector potential is around the solenoid. It also has got azimuthal symmetry about the axis of the solenoid. But look at the relative orientations of the particles which are going from one side of the solenoid compared to the other. On one side it is going in the direction of the vector potential, in the other it is going opposite to that. So, that is what creates a phase imbalance. Okay? and it is this phase which comes into the expression for the Feynman propagator. Okay, we have already seen that Feynman amplitudes are the same for all the infinite paths, but they differ in phases. And if this difference in phase is coming about because of the interaction of the particle with the vector potential. This is not to say that this has nothing to do with the field B. This has to say with the fact that the field B is 0 outside the solenoid, not that it is not there. It is there, it is somewhere. Where is it? It is confined inside that cylinder. Okay? And because the field is there, there is a flux, and this flux will appear explicitly in the expression for the Aharonov-Bohm phase. Okay? So, the field is in some sense related, not that it is irrelevant, but it does not go into the estimate that it does not go into the Schrodinger equation itself anywhere. So, this is the idea we are going to discuss in today's class, and we wrote the Schrodinger equation for this particle in the electromagnetic field. We consider the magnetic vector potential to be set up in a region of electromagnetic vacuum, and now you have the presence of the magnetic vector potential because of this current in the solenoid. Okay. The vector potential has got this azimuthal symmetry. The flux is a surface integral B dot ds, but it is only the area which is inside the solenoid. So, A is the radius of the solenoid. The expression for the vector potential A is the one which is appropriate for rho greater than A, which is outside the solenoid. That is the region of interest. That is the region which the particles are passing through. And we wrote this expression in cylindrical polar coordinates, and then it looks like a one-dimensional Schrodinger equation, not because it is a one-dimensional problem, but because we have reduced it to we have exploited the azimuthal symmetry. You have to be a little bit careful with the notation, because phi has been used to denote three different things, and these are the three fonts in this red box. The first one is the azimuthal angle, the middle one is the electric scalar potential, and the third, which is like the uppercase phi, the last one is the magnetic flux phi. All right. So, there are three letters or three fonts which we have used for phi. We also discussed the gauge invariance properties of the Schrodinger equation, and we recognize that when the vector potential is changed from A to A prime, which is A plus del chi, chi being the gauge function, the scalar potential, the electric scalar potential goes to phi minus del chi by del t, and the Schrodinger equation is invariant with the transformation which involves a phase factor, which is q over h cross times the gauge function, and q is the charge. So, that is an important aspect of this gauge transformation, that the charge comes in the expression for the gauge invariance along with the transformations of the electric vector potential and the magnetic electric scalar potential and the magnetic vector potential. So, this is what you have. So, once you have A, you need the last term which requires A square. So, that comes out as phi square, okay, and you put everything in terms of the flux now, and you have got the Schrodinger equation. written in terms of the magnetic flux. So, if you look at this equation, this is nothing but a linear differential equation with constant coefficients. Okay? You can simplify it, you can deal with the equation at the top, but then you have to write too much because you have to write q phi over 2 pi h cross every time and so on. So, you simplify the notation a little bit by introducing these auxiliary or ad hoc intermediate terms beta and epsilon. That makes it easy to write, not because it introduces any new physics nor any big mathematical convenience. Okay, it is exactly the same thing, it is only a notational convenience. So, you introduce epsilon and beta, and now you know how to solve this. Equations of this kind you would have solved umpteen number of times. So, it has got a solution which is simply a e to the I lambda phi, right, where lambda is, you will get a quadratic equation, and the solution is beta plus or minus root of beta square plus epsilon in the notation that we have used. So, this is easy to get, all you have to do is to put it in and check it out, please do it. So, this is your solution to the differential equation, and that gives you the tool to determine what is the energy eigenvalue of this problem, because square root of 2 me is appearing explicitly over here. Okay. You also have the uniqueness property of the wave function. So, if you are looking at the wave function at some point and then go around and come back to the same point by adding the 2 pi to the azimuthal angle, the value of the wave function should not change, and that ensures that there is quantization. Okay, there is discreteness which is coming out of this uniqueness condition. So, the term in the box involves the energy, but the energy can only be such that this equation is satisfied, in which n must be a positive or negative integer. So, n can be either a positive or negative integer. It can of course be 0, which is both a positive integer and a negative integer, right. So, you have n, and you can rearrange this to get the energy itself, and the energy turns out to be given by this constant, which of course has the flux. But if the flux was 0, this energy would be the same irrespective of n being plus 1 or minus 1 or plus 2 or minus 2. The plus and minus signs would not matter. Okay, they would get washed out in the n square, but they do not get washed out because you have n minus q phi over 2 pi over 2 pi h cross square. Okay, so you need the difference. In other words, the magnetic flux is removing the degeneracy that was there in the absence of the flux. Okay. So, what the vector potential does is it is removing this degeneracy, and you are beginning to see, I had this in some of the earlier diagrams also, the fringes which are shown behind the detector are the familiar Young's double slit dark and bright fringes, but then you see another set of fringes which is shifted from the original one, and that is what the phase difference is contributing to. So, we will see exactly how this comes quantitatively. Notice that the spectrum's degeneracy is lifted by the flux, but if the value of the flux is such that q phi over 2 pi h cross is exactly an integer, then you recover the original spectrum. You will have essentially the same spectrum as without the flux. So, you have the same spectrum with the flux as you had without the flux, not for any arbitrary value of the flux, but for such values of the flux for which q phi over 2 pi h cross is an integer. Okay? And that is the case of interest as it will turn out. And this is similar to the problem of a charged particle which is constrained to move around a ring. And if you solve this problem, you do have this degeneracy. This is the same problem as what we discussed above in that solenoid diagram, except for the fact that there is no vector potential over here. And this is the point I was making, that when you add the vector potential, okay, you can do so because of the current in the solenoid. But what also happens when you switch on the current in the solenoid is that there is a flux inside the solenoid. And as a result of this, the eigenvalues are now not degenerate. So, whatever degeneracy was there in this charged particle on a ring problem is lifted by the vector potential. Okay? So, we know that this is valid for n equal to plus or minus 1, plus or minus 2 and so on. So, you can write it as plus or minus n whole square, and you can write it for the 2 plus n and minus n's differently, and then you see that the E plus and E minus are different because the minus 1 square gets washed out. Okay? And essentially you see that the positive n has got a slightly lower energy than the negative n. So, the positive n are the particles which are coming on this side along the vector potential, and the other ones are those which are travelling behind, and if they are travelling behind, then the vector potential is directed in the opposite direction. Okay, so you need to keep this in mind, that in one the flow of the particles is along the direction of the vector potential, and for the on the other beam it is opposite to that. And this is interesting because the value of the field itself is 0 in that region. Okay? So, the energy depends on the flux and on the magnetic field, but the field itself is 0. So, this is like, you have a change but you do not have a change. It is because of the field, but what is the value of the field there? It is 0. All right. So, this is similar to, it is in this sense that the analogy of the Foucault pendulum was brought about. That okay, you carry the pendulum, all right, you have not changed anything, but you come back, take it from the North Pole to a point on the equator, then to another point on the equator, and go back to the North Pole, and you find that the plane of oscillation, which has not changed anywhere in the middle, but ends up changing at the end, right. So there is a change but not a change. So this is the interesting thing about the adiabatic changes. So now let us examine the Schrodinger equation, and here you have got a potential term which may or may not include the electric scalar potential phi, the middle phi that we used in the 3 phi's, okay, in our notation. So, that may or may not be included. You could begin with a vacuum, but if it is not vacuum, it does not really matter very much. It does not do any difference to this analysis. So, now you have two Schrodinger equations, one for the vector potential A prime and phi prime, and the other for the vector potential A and phi. And these two are related to each other through the gauge function, the gauge transformation, A going to A prime and phi going to phi prime. And what this transformation does is to scale the wave function only by a phase factor, which involves the charge, which is e to the iq over h cross times the gauge function. Okay, so this is the gauge parameter. And the phase you can see, because chi is a function of local r and local time, so it depends on that. So, this is the Schrodinger equation that we have, and we have learnt already that you can write this as the integral A dot dr. I think I should have had a vector sign on top of A, which I missed out. Okay. So, A is the vector potential here. Okay. And this integral will be path independent in whatever region the curl of A is also 0. Okay, it is not guaranteed to be so in other regions, but whenever the curl of A, you can see it from the Kelvin-Stokes theorem also. Okay, and given psi by this, I think I will fix this vector sign on A. I remember I was correcting some answer scripts of students when he was a very young boy, and my son was a very young boy. He complained that, "Daddy, when you make a mistake, you just go and fix it. And when your students make a mistake, you give them a 0. So he thought it was very unfair. So if I have students who do not put a vector arrow on top of the vector, yes, I do give a 0. But when I do it myself, I just go and fix it. All right. But we can deduct some points for this. So you have this integral which is path independent in the region where its curl vanishes. And now we can ask what is its gradient. So this is the gradient of a product of two functions. So it is one function times the gradient of the other plus the other equivalent term that comes out of this. G is a function of r. So you will have the gradient of G coming in the first term, right? And the gradient of G, G itself is an integral, and now you are going to take its differential, so you will get the integrand. Okay, so you get q over h cross A. So that is the gradient of G. You can put it in the expression for del psi. Move the first term on the right to the left with a minus sign. Okay, that is all that we have done now. Notice that psi prime is the same as the term in the parentheses in the last term, that is nothing but psi prime. Okay. And notice further that now on the left hand side in the second term you have e to the igr and also an e to the minus igr, and they are coming only as multiplicative terms. So these two terms will cancel each other. So we can strike them out and then carry what remains to the top of the next slide. we have cancelled these terms and we are left with a somewhat simpler expression. And on the left side, you can write it as an operator equation in which the second term is simply that factor multiplied by the unit operator essentially. Okay? So, you have an operator operating on the operand, and then you have the right hand side, which is the gradient of psi prime, not psi. Psi prime is the solution to the Schrodinger equation with the transformed electromagnetic potentials, okay, multiplied by the phase factor. And you operate on this equation. Essentially what you take is take the divergence of that. So, take del dot this term and add to it this minus iq over h cross a dot the same term. So, that on the left hand side you will have the square of this operator, but you do the same to the right hand side as well. Okay. So, you have got the left hand side and the right hand side. On both sides you operate by the operator which is in this red color. If there was no vector potential, it would be like taking the divergence, but you have that vector potential. So, you take the divergence and add another scalar product, okay, and scale it by minus iq over h cross. That's what, it's as simple as that. So, on the left hand side you have got the square of this operator. On the right hand side you have got now two terms. One is the divergence of what was originally on the right hand side, and the second term involves the scalar product of A with the gradient of psi prime, okay, and then it is multiplied by this iq over h cross and of course the e to the igr. You can see all the terms. You are comfortable? Yeah. Actually this physics sometimes gets lost if you are spending all the time writing these things on the board, because you are not following these things, you are just looking one term at a time. You need to see the whole term to see what is really going on. So, if you look at the first term, which is this. This is the divergence of a product of a scalar function which is e to the igr times a vector function which is del psi prime. So, this is the divergence of this product. So, it will be this times the Laplacian of psi prime plus the dot product of the gradient of e to the igr, which is this, with del psi prime. Okay? Got it? So, this is the divergence of this term in the bracket, consists of these two terms, one involving the Laplacian of psi prime and the other involving the gradient of g, but we know what they are. So, I brought it to the top of this slide. The gradient of g we have learned is q over h cross times a. So, we can put it in. So, put the gradient of g here as q a over h cross, and this comes with a plus sign here because of this, and you have the q a over h cross with a minus sign. I is and everything else is common in both the terms, so you can cancel them, and now you have the left hand side equal to only this term, which is here, which is also equal to this because I square is minus 1, right. So, this is the end result that we get from this operation. Keep track of the fact that you have psi on the left hand side and psi prime on the right hand side, and these two differ in phase, they do not differ in anything else. So, now you have got the Schrodinger equation with the vector potential. And the result from the previous side tells you what happens if you operate by the square of this operator, which is in blue, to psi, you get the Laplacian operating on psi prime. So, what is in blue can be replaced, they are completely equivalent to each other, which is what we have done now. Okay? You not only slides, but you need color coded slides. It really makes it easy. Okay? Because then you can really concentrate on the physics without having to do simple mathematics which an undergraduate student can do very easily, or even a high school kid could do. So, now you have got this psi and psi prime, which are the same except for the phase, and you write the psi on the left hand side in terms of psi prime with the phase, and then you have got this phase common in all the three terms which are there in the equation. So, you can strike them out, and then you are left with the Schrodinger equation without the vector potential. You immediately recognize that this is nothing but the Schrodinger equation without the vector potential. So, in other words, this e to the IGR is coming out like the Aharonov-Bohm phase. Okay, that is the phase difference which the vector potential introduces. So, if you do this experiment, Young's double slit experiment, without any current in the solenoid and with the current in the solenoid, you are introducing a vector potential, and what this vector potential is doing is to introduce a phase in the wave function. So, this is the Aharonov-Bohm phase effected due to the gauge transformations. Okay? So, the Schrodinger equation with one set of potential and the Schrodinger equation with another set of potential are completely equivalent. You have got the same eigenfunction, which however differs to some extent, not in details, but it does differ in the phase, which is the Aharonov-Bohm phase. Okay? So, now let us estimate what this phase is, Aharonov-Bohm phase is. So, this we know is given by this integral, and A dot dr is what you have to add up over the path over which the particle interacts with the vector potential, and it interacts along the direction of the potential on one side of the solenoid and against it on the other. Okay? So, there is a front beam, the beam which is on our side, there is one beam on our side of the picture, and the other beam is behind the solenoid. So, what is on our side is going in the same direction as the vector potential, and on the opposite side it is going against the vector potential. So, A dot dr, dr is the vector displacement, and delta r has got opposite signs, and on one side it goes in half a circle, in the other it goes in half a circle. Okay? So, if you draw a line from the center, this line is going to sweep an angle of pi, okay, on one side, and also pi on the opposite side, but with a minus sign. Okay? So, the two terms pick up opposite phases which are plus or minus beta. It will be equal in every other sense except for this sign. Okay, there is no other difference, and except for the sign it is the same, and you have to determine this integral A dot dr. What is A? A is the flux over 2 pi rho times E phi. Rho is greater than the radius of the solenoid. It is completely outside the solenoid. The curl of the vector potential is 0. The magnetic field is 0. And the vector potential itself is phi over 2 pi rho times E phi. The flux itself is BA square. And now if you evaluate this integral, notice that the displacement delta r is rho delta phi, okay. So the rho in the numerator and the denominator cancels. Now in this integral the flux comes out as a constant. Flux is only what is inside the solenoid, so it has nothing to do with this region at all. 2 pi in the denominator also comes out as a constant, so phi over 2 pi comes out as a constant, so you have q times phi over 2 pi, and then you are integrating d phi over the semicircle in the front and the semicircle on the back, and that will turn out to be plus or minus phi, plus or minus pi, okay. It is going on the semicircle, so it will be plus or minus pi. So the particles trace trajectories over which the angle which is swept is plus or minus pi. So now this Aharonov-Bohm phase turns out to be q phi over 2 pi h cross, which is coming from the constants in that integration, and plus or minus pi, which comes from the half integration over the semicircle over which the particles interact with the vector potential, and that is plus or minus q phi over 2 h cross, right. So that is the phase difference, and that is the one which is going to impact the interference pattern on the detector, because these phases add up in the Feynman path integrals. So one is plus, the other is minus. So the difference is q phi over h cross, okay. Half of this comes with a plus sign, the other half comes with a minus sign, and the difference is q phi over h cross, and this is what I call as the Aharonov-Bohm phase difference, okay. Now this phase difference is what will impact the interference pattern, and depending on what is the value of this phase difference, the interference patterns will shift. And Uday has developed a nice simulation program which shows a Young's double slit experiment with the flux and without the flux, and he shows this interference, which is very nicely, it's a nice pedagogical article he is writing up. And this phase is actually nothing but the Berry phase. And to see how it is the Berry phase, okay, we did not define Berry phase as the Aharonov-Bohm phase. We defined it by what is at the bottom of the screen, that the Berry phase is I times this integral, okay. This was, I think, in the previous class or in the class prior to that, right. So we have to show now that the Aharonov-Bohm phase is the same as the Berry phase. So we will have to take the wave function, take its gradient, right, and then determine this integral which you see in the expression for the Berry phase, and we hope to discover that it will turn out to be the same as the Aharonov-Bohm phase, which is q phi over h cross. So let us see what happens. So you consider a particle in a box, and you carry this box around an axis through a full rotation. So there is something that you are changing geometrically, right, but then you complete that and come back to the original geometry, and the potential inside that box, let us say, depends on the particular point in that box. So you consider positions of points inside that box in relation to the center of the box, which is this difference vector small r minus the big R, and write the Schrodinger equation, right? And the solution depends parametrically on the value of R, because that R can be anything, okay, it can be a few millimeters, few centimeters, whatever. And we know how to write these solutions. With and without the vector potential. So, without the vector potential, you have not done anything to the potential at this point. And this psi prime will then depend on the difference vector rather than the absolute values of small r and capital R, only the difference really matters. But do register this point, because when you are looking at this difference vector, it is small r minus the capital R, and the sign of the small r is plus and the sign of the uppercase R is minus. So, they come with opposite signs, and this has got some importance, because we are going to have to take the gradients, and that is where the difference will come. Now, we will carry the box around the axis of the solenoid, okay, through a complete loop and come back to the same point, and then evaluate what this Berry phase will turn out to be. So, essentially we have to evaluate this integral. So, we have got the wave functions. We need the gradient with respect to the uppercase R, okay. So, gradient of psi itself is the product of e to the ig times psi prime, right. So, take the gradient, and the gradient with respect to the uppercase R on the left hand side, and then on the right hand side I take the gradient with the lowercase r vector. So, that will pick up a minus sign, because the two appear in this context with opposite signs. So, now on the right hand side I can take the gradient with respect to the lowercase r instead of the uppercase r, and when I do that I must use a minus sign, okay. So, now I take the gradient with respect to the lowercase r, and what is that? I have got the gradient of the first function times the second term, and then the first function times the gradient of the second term, okay. And the gradient of the second term, I can take it, that term will come with a minus sign if it is with lowercase r, or with a plus sign if it is with respect to the uppercase r. So, you can play with that. And in the first term you have got psi prime times the gradient with respect to the lowercase r of the e to the I q over h cross times the phase, right. So, this is what we get. Notice that there is g in both the terms. So, I can extract that as a common factor e to the ig, and then I will be free to use this result later on. So, I want to keep it at the back of my mind, which is suggested by this multi-starred star, okay, right. We are comfortable with this? Very good. watch the subscripts and the gradients, they are important. Okay. And now what goes into the Berry phase is the integral of an integrand, and that integrand involves this inner product. So you need the projection of this gradient of psi on psi n. In other words, you have to determine this integral. I have written it in the Dirac notation and now in the usual de Broglie-Schrodinger notation, okay, so that we know what is it that we have to integrate. And in the de Broglie-Schrodinger equation, we have got the complex conjugates. So what was e to the ig in the Dirac comes out as e to the minus ig in the de Broglie-Schrodinger, and the psi prime comes out as psi prime star, and then this is the volume integral that we have to determine, right. This is the volume integral. The gradient of psi we determined on the previous step, which we marked by this multi-starred star. So we can put that result here. Done. Okay. We have simply substituted that term. Now you have e to the minus ig and e to the plus ig, which simply come as multiplicative factors. So you do not need to write them. And what is inside this curly bracket, in this beautiful bracket, in the blue terms, there are actually two terms corresponding to which I write two integrals. Okay. What is the first integral? First integral has got this minus I over h cross here. Okay. And then you have got a constant vector potential. And then you have got this integration over whole space of psi n prime star, psi n prime, that is like the normalization integral, it will turn out to be unity. Okay. And then in the second term, I multiplied this by minus I h cross and divided by minus I h cross. Okay. In the second term, I multiply this gradient with minus I h cross so that it looks like the momentum operator. Okay. Because minus I h cross gradient is the momentum operator. But having done so, I need to undo it by dividing it by minus I h cross. So multiplication by plus I over h cross is the same as division by minus I h cross. And what I have in the second term is nothing but the expectation value of the momentum operator of the full Hamiltonian. But the momentum and the operator and the Hamiltonian do not commute. Okay. So you will need a full superposition and this expectation value of the momentum operator will vanish. So the second term vanishes and the first term exploits the normalization integral, and you get this term which we will put in the expression for the Berry phase in the integrand, and that turns out to be minus I over h cross q times the vector potential, right. And this will go into the integrand which we have used to define the geometrical phase. This is the geometrical phase and we have got the term in the integrand. So put it in, right. And get the common terms out. Now you have got a line integral over a closed path. And where is this path? This is the path outside the solenoid where B is 0. Okay? So you have got the surface integral B dot ds, and B is not contributing in the region of the path. The B dot ds, what are you doing? You multiply the magnetic field by the surface element and then add it up over the entire surface which is in that loop, of which only the region in the solenoid is contributing, rest of it is 0. But this part is not 0, what is inside the solenoid, that is giving you the flux B dot ds. Okay? So, that part contributes the flux which is phi, and your result is q phi over h cross, which is just what you got from the Aharonov-Bohm phase. So, the Berry phase turns out to be q phi over h cross. The Aharonov-Bohm phase which we saw earlier is also q phi over h cross, and you essentially have the Aharonov-Bohm phase which is the same as the Berry phase. Okay, it is therefore an example of the geometrical phase, and this is from Uday's simulation. So, on the lower side you have got these fringes, and then there is a dashed curve which shows how they shift when you change the flux, because the path difference is changing. Okay? This is the path difference which is coming in the Feynman propagator. Okay? And when this phase difference is 2n pi, there will be no change, and when this phase difference is 2n plus 1 pi, then the bright and the dark fringes will interchange. Where you had the bright fringes, you will have the dark fringes, and vice versa whenever q phi over h cross, phi being the flux, is 2n plus 1 times pi. Okay? So, this is the Aharonov-Bohm phase which gives you an illustration of the Berry phase, and you see that it is this Feynman path integral approach which gives you a very convenient, easy, direct, straightforward interpretation of the Aharonov-Bohm effect, which is essentially a quantum effect. There is no classical analog for this, okay, because classical electrodynamics relies on causality, okay, whereas this effect is coming from the geometrical phase in the solution to the Schrodinger equation. Okay? So, the Berry phase and the Aharonov-Bohm phase are exactly the same, and if you see, look at the phase angle, it has the flux. And why is there a flux? Because there is a magnetic field. B dot ds is the field, but you are integrating B dot ds over an area which is larger than the cross-sectional area of the solenoid, and it has to be, it better be larger, because it is outside the solenoid that the interfering beams are going through. Okay? So, it does go through that region, but when you add up the surface integral B dot ds, it is over this entire surface, which you can think of as the part of the surface area which is inside the solenoid and the part which is outside. The part which is outside the solenoid contributes 0 to B dot ds. There is no magnetic field there. But what is inside is what contributes to the flux, which is phi, which goes into the Berry phase, which is nothing but the Aharonov-Bohm phase. So, thank you very much. I can take a few questions.
Is there any threshold value for the magnetic field so that only we will observe this Aharonov-Bohm effect? Like beyond that, we will observe, like below that, is there any? Or like
no, if there is a vector potential, it will contribute, because whether it is detectable depends on how you have set up your experiment. Okay? because the intensity distribution pattern is going to change, okay, and that depends on the sensitivity of your detectors and so on.
And if
So,
we
if you can detect that, if you have sensors, you can do it, it will be there. So, that does not depend on any physical principle, but depends on how you have set up the experiment. Yes.
and like if we change the direction of current, will the pattern will shift down?
Yes,
That will happen.
yes, 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 it does. Actually, in the simulation that Uday has set up, you should do this experiment, because there you do not need a very good experimental apparatus. All you need is sit in front of the computer and change the direction of the current, change the you can change the charges if you like, you can change, because it depends on q phi by h cross, so it will also depend on the charge. So, you can have an electron charge with a minus sign, you can have a positron charge with a opposite sign, and you will see this effect of the sign of the charge. You can change the value of the charge, okay. You cannot change the value of the charge of an electron in an experiment, but you can do it in Uday's simulation, okay. And if you change the value of the charge, you will still see these shifts. So, that is why we theorists always say that we can do what experimentalists cannot do. But that is nice, because you can test your models. You can test your models. We do that when we study the electron correlations all the time. We switch off some terms, put them back in the calculation, and see how they impact the result of the calculation. So, okay, thank you.